Okay, so when we talk about our centripetal speed or angular speed, what we know is that the difference between angular and linear or tangential is how far you are from the center of rotation. And so if we're rotating like so, draw that a little better, we know that a person rotating here versus a person rotating here are going to have different linear, or what we call centripetal speeds, but they'll have the same angular speed because this person here is covering less meters than this person here, as you can just see that. So the linear speed, if they're going to stay rotating in the same line, the speed here has to be greater than the speed here linearly because more meters are being covered per time period than here. But they're both covering the same angle, so they both have the same W, or angular speed, or omega, but they have different linear speeds. And we also refer to linear as tangential. And so as we go through here, we're going to take a look at those. Now, what we're going to do is take our angular displacement, which is arc length over r, radius, and we're going to divide both sides by time. And we do that. This is our angular speed. And this, if we take our arc length and we just take it as it gets smaller and smaller and smaller, becomes a point, that is the speed at that particular point. That would be our tangential velocity. And so we relate our linear with our angular by deciding how far are you from the center. And that makes sense. The farther you are from the center, the faster you're going to go linearly, even though you all have the same angular speed. So for instance, if I wanted to say, all right, well, I have an angular speed of this little microbe as 31.4 radians per second, and I have a radius of 0.006 meters, what I can say is the tangential speed then, my tangential speed then is simply going to be r times w. And that radians per second becomes meters per second. Our radian sort of disappears. We don't need it anymore, and so it just leaves. It's like the room of requirement in Harry Potter. When we need it, it's there. When we don't need it, it's not there. Okay. So we can switch between linear, meters per second, and radians per second, just knowing how far is the object from the center. We can also then take our newfound equation here and say, all right, well, if I have a velocity or change in velocity or change in tangential velocity over time, that's just our basic acceleration. Now we're going to call it tangential acceleration because it's going to be caused by a force that's applied tangentially. And if you're in class, you see me kind of hitting the tire, and just think about how you'd hold a tire that, you could hold the middle and you see how you could speed it up. I'd apply a force, a tangential force, and that tangential force would cause a tangential acceleration. So when I do that, divide both sides by t, we know that angular speed over time is alpha, and tangential acceleration would just be v sub t over t. And so we get this equation right here. A sub t is equal to r times alpha. So again, we're relating angular to linear with how far you are from the center. Now, the other important thing is to know, why does this change speed? And the reason that this is going to change the speed, and I'm going to write this, I don't know if this actually comes through, so I guess you'll just have to replay this over and over again, is this displacement right here. I'm going to draw it in red. This is the displacement. So that's the little bit of arc length, and we can take it as the limit approaches just a point. But this force is parallel to displacement. And if you remember, that should maybe hopefully ring a few bells. That force is parallel to displacement. And because the force is parallel to displacement, work is done. Now, that's the only way work is done. If work is done, work is equal to the change in kinetic energy, the work kinetic energy formula, which is equal to 1/2 mv squared, final minus initial. And so we do change the velocity with this type of force. And you can see that in class. I've done that in class, but think about how you'd speed it up. Or if you'd slow down a tire, you'd put your hand to it, and you just put your flat hand against the tire, and you'd apply that force to slow it down. Okay, so again, you can simply find your tangential acceleration just died here. Plug it in. By taking alpha times r, so taking that 0.5 radians per second squared, 6.5 meters, and getting units of meters per second squared. And so 3.25 meters per second squared. So we have our tangential and our angular. Now, from chapter 5, because we just did this formula we used in chapter 5, because we know that we can make some substitutions, and we also have this formula as well. But centripetal acceleration, unlike tangential, this is tangential acceleration, is toward the center. Those were always the center forces like gravity or normal or tension or friction. Something was pulling you toward the center. That's your centripetal acceleration. Now, this is not responsible for speeding up or slowing down. This is only responsible for changing direction because it is perpendicular to displacement, displacement being the little red right there. Because it's perpendicular, no work can be done, therefore no change in kinetic energy and no speed. So it's the exact opposite argument of before. So again, just kind of going back to centripetal acceleration from last chapter, and depending on what you're given, and here we're given the linear speed. So we just simply take that and divide. We're going to get a centripetal acceleration of, let's see, 8.05 meters per second squared. Now, what's the tangential acceleration here? Well, if there's a constant speed, it's nothing. Okay? So if it is speeding up, then we would have a tangential acceleration, and then we're going to have to take both of them into account. So how would we take both of them into account? Well, they are going to be perpendicular. And so I have a sub, like I just drew, a sub c here, a sub t here. So I'm going to go ahead and draw, I'll bring a sub t over just parallel. And what we end up having is an angle, and I'm going to call it chi. I'm going to do this as an angle. I don't want to confuse it with theta, because theta is our angular displacement, and I just don't want to confuse that. This is something different. This is an angle between a sub t and a sub c, directed radially inward. And so the tangent of chi is going to be a sub t over a sub c. But the biggest thing here, angles are good to know too, but the biggest thing here is if you want the total acceleration, not to be confused a sub t with total, it's tangential plus centripetal squared, and that's going to give you your total acceleration. Now, if an object isn't speeding up or slowing down, then that's going to be 0. Okay.